Our guest today is Phil Christensen. He's a professor of geology at Arizona State University and my former boss. He runs a research center that does daily operations for several instruments on board Mars spacecraft, and he's just sort of an all-around smart guy. So he's here to talk to us today about remote sensing.
Greetings. It's a pleasure to be here. As Michael said, I'm at ASU. I'm a geologist initially, then became a geophysicist, got interested in Mars, and unfortunately to date have then had to become interested in remote sensing because that's the only way we have of studying Mars. So I've spent most of my last 20 years or so building a variety of instruments. I thought I'd start off by sort of summarizing the last 20 years of my life. A sort of a frightening statement to say these 4 machines are summarize what you've done for the last 20 years. But these are instruments about yay big, mostly infrared, and we've sent all of them to Mars. And so what I'd like to do today is talk a little bit about just a quick introduction to sort of the physics of remote sensing, so we're sort of all on the same point, and then show a few examples, and then just talk about some applications. I'm reasonably well aware of what you guys are doing in terms of remote sensing with Visible and Google Earth, et cetera. What I want to try to do today, at least at an introductory level, is discuss some of the other aspects of remote sensing, other wavelengths, the importance of time, et cetera, to see what other information one could get. And if nothing more, just sort of set the stage a little bit to get you thinking about, oh, okay, well, maybe we could do that for the Earth, or maybe there might be something useful there, or maybe there might be an end result that could be incorporated into the things that you're doing. Okay, so just pardon me, but I'm going to, not knowing the audience really well, I thought I'd just give a little bit of overview about what do I think remote sensing is, and what's some of the key physics behind it. And just to summarize, in the simplest case, remote sensing is just using images. I mean, everyone in this room has been doing remote sensing since you were born. Your eyes are probably the single best remote sensing instruments ever designed. Your ears aren't bad either. And so in the simplest case, we're collecting visible light, spatial patterns, temporal variability, and using that information to construct a 3-dimensional model of the world around us. The next level is to take full use of the electromagnetic spectrum. Our eyes evolved to focus on the light put out from the sun, but there's a whole spectrum of electromagnetic energy that goes beyond visible. I want to talk a little bit about that. And then, to me, what remote sensing really is about is extracting quantitative information from all of that information. Not just the patterns that we see, but quantitative, compositional, physical information about the nature of the surface, whatever planet it's on. Just going back to high school real quick, remind everybody, visible light, about 1/2 micron. I'm going to mostly today be talking about near-infrared and thermal infrared, which have wavelengths of about 10 microns. But obviously, you can do everything from gamma ray and X-ray remote sensing all the way out into radar and microwave. So there's this, whatever that is, 9 orders of magnitude of variation in the wavelength of light. And to say that we use sort of from 0.3 to 0.7 microns out of that 9 orders of magnitude is a pretty limited piece of the electromagnetic spectrum that most of us use. And I'll be talking a little bit today about both reflected and emitted light. Again, most sensors, visible light sensors, use the sun as a source, and they look at the reflected or scattered light that comes off of surfaces. We can have other sources of energy. We can illuminate the scene with microwaves or radar, and we can certainly look at just energy that's emitted. Every object which is not at absolute zero is emitting energy. All of you are emitting a lot of energy right now, and we can sense that and make use of that emitted part of the spectrum as well. I think I'll get through the word slides here pretty quick and then get down to looking at some images. Just again, as a quick review, remote sensing is typically broken up into two broad categories. One is active remote sensing, where you're actually providing a source. And that source traditionally has been radar or LiDAR. So you are illuminating the scene. That has some real advantages because you can control the wavelength, you can control the illumination angle, you can control how much power you put out, you can control both the observing and illumination geometries. You can work when it's night, you can work when it's cloud covered. So active systems have a lot of benefits. Obviously, they take a lot more energy. You have to actually illuminate the source yourself. The other piece of part of remote sensing is the passive side. And this has traditionally been one of the largest parts of remote sensing. And I think you can break it up there again into three basic categories where the physics of what's going on is fundamentally different. You can look at very high energy interactions, and that would include things like gamma rays and X-rays. Here on the Earth, we're shielded by our atmosphere. Not very many gamma rays and X-rays get to the ground. But on airless bodies like Mars, there's a lot of cosmic rays, a lot of high energy sources that get to the surface, excite the atom at the nucleus level, generate gamma rays and X-rays, which we then observe. And we can tell literally what elements are on the surface by looking at the spectrum of gamma rays that come off. So there the interaction is going on at the nuclear level. What I'll call moderate energy is ultraviolet and visible photons. Those have enough energy to excite or interact with the electrons that are that are surrounding the nucleus. So slightly lower energy, but there, as we'll see in a minute, we're actually exciting electrons to different energy levels. And then the final one is sort of the low energy infrared and even out into the microwave. Now the energy of the photon barely has enough energy to cause these bound atoms within a structure to vibrate, okay? So each one of those then, based on the energy of the electromagnetic wave that's hitting the material, interacts at a different level. And each one of these, X-ray, UV vis, infrared, is providing a unique piece of information about the atomic structure of the material that it's interacting with. And I'll spend a couple minutes talking about that. Okay, some basic physics to remind everyone. Light, of course, is an oscillating electromagnetic wave that has a wavelength, a velocity, the velocity of light, and a frequency, and those are very closely related. Velocity equals wavelength times frequency, okay? And frequency, as we'll see in a minute, is important. The frequency of the light depends a lot on how it is going to interact with the material. I think one of the most useful equations to keep in mind is E equals h nu. The energy that a photon or a wave contains is directly proportional to its frequency. So that gets back to what I was just saying in the last point, that shortwave, high-frequency photons carry a lot of energy. Long-wave, low-frequency photons carry much less energy, and therefore they interact at the atomic level very differently. The other thing to keep in mind is electromagnetic waves, as the name implies, are oscillating electric and magnetic fields. And so if light is an oscillating electric field, and I interact with something that has charged particles, either electrons or nuclei, that electric field can interact with those charged particles. And it's the nature of that interaction then that causes light to be absorbed, okay? It's the reason why things have color. It's the reason why water heats up in a microwave. It's sort of the process by which light interacts with material. It's the fact that I've got oscillating electric fields interacting with charged particles, and those charged particles are going to move when they're bathed by that electric field. And so you convert the energy in the wave into the kinetic motions of the material. Okay, just a couple more points here. Similarly, at the same time that these electric fields are oscillating, the atoms in any crystal structure are also oscillating. Okay, they're bound in there by the forces that are holding those atoms together, but they're certainly not, balls on sticks like you see in a chemistry class. A much better model would be balls on springs. So I've always been trying to find somebody who would make a beautiful model of a complex molecule where you have these little masses and they're bound together by springs. All those masses are free to move around, okay? And just like in any system of masses and springs, the motions of that system are going to have resonant frequencies. They're going to vary with the mass of the atoms, and they're going to vary with the strength of the bonds, okay? So in any given crystal structure, you've got these masses, and they're held together by these bonds. Every one of those pairs of atoms has a specific resonant or harmonic frequency that it's going to naturally want to vibrate at, okay? And that's then sort of the key to how light is going to interact with this material. Because what happens then is if I have this oscillating electromagnetic wave that's coming along, if the frequency of this oscillation, say some frequency nu2, matches the frequency of this harmonic resonance frequency within the material, then this electric field will excite these charged particles, cause them to move, and in the process, reduce or subtract energy from that wave so that when the wave comes out the other side, it's reduced in amplitude, okay? So it's just a fancy way of saying this light is absorbed by this material. But the thing that makes it important here is if I have a wave that's at some other frequency that's different from this resonant frequency of the material, then that wave tends to pass through the material more or less unchanged. Okay, there isn't a strong interaction, and so the light can come out. So in this particular process, and you can imagine that if I took a spectrum of white light and illuminated a surface, the waves that come out the other side, the spectrum that comes out the other side, I'm going to be missing those frequencies that correspond to these natural vibrational frequencies within the crystal. Okay. Let me come back to that. Okay, so that's two pieces of basic background. The third piece, if we're going to talk in particular, I want to focus now on sort of infrared spectroscopy. I want to talk about the emitted part of remote sensing. And to do that, we need to talk about the source function, what energy is being emitted by a material. I'm sure you're all, at least at some level, familiar with the concept of a black body curve. Planck, back in the early 1900s, derived this equation from sort of first principles of physics using the quantum nature of the energy structure of materials, and was able to predict then what we observe, and that is that the amount of energy emitted by material varies with wavelength. So here I'm showing wavelength in microns and temperatures, 0 degrees centigrade, 20 degrees centigrade. So this blue curve is basically a spectrum of the light that you're giving off, okay? All of you are emitting, all of you are at about 20 degrees C, maybe 30 degrees C, and you are emitting energy, and the energy that you are emitting is peaked at about 10 or 12 microns, okay? If I were to heat you up to 6,000 degrees C, how would the shift, what would your peak wavelength be if you were 6,000 degrees C?
Somewhere in the visible.
Somewhere in the visible. Okay, the surface of the sun is 6,000 degrees, and these exact same curves hold just as well for those temperatures as our temperatures. And so if you plug in 6,000 degrees C, two things happen. One is there's a lot more energy emitted, and the wavelength at which it peaks shifts to shorter and shorter wavelengths. So the sun is peaked down at about 0.5 micron, which is exactly why our eyes have evolved to be most sensitive to light at about 0.5 micron. As we'll see in a minute, the world is a whole lot prettier place in the infrared than it is in the visible, at least the natural world is. Rocks and minerals are. And we would be, as a geologist, I would be much better suited with infrared eyes able to look at the world than with these crummy visible ones that I'm stuck with. But the fortunate thing is we can build detectors that allow us to see in the infrared. Okay, so materials are emitting energy, and they're doing it in an ideal world. They're doing it as predicted by Planck from his famous equation, and the energy coming off of an ideal surface would look something like that. Okay, but now we have to, but in Planck's world, things weren't bound together. There were no bound atoms. Everything was just free to move around. It was not bound to anything else. When I start creating a crystal structure where I have atoms bound together, then we have these harmonic motions, these preferred frequencies, and now the light that's being emitted is no longer follows perfectly the Planck's function. We start to see these absorption bands, which are due to the vibrational motions of the material. That upper curve shows the black line is the idealized Planck function. The red curve is a measured spectrum of a mineral, in this particular case, just a nice simple quartz crystal. And then typically what spectroscopists do is they take the ratio of those two, create something called the emissivity. The beauty of the emissivity is it's independent of temperature. If I just measure the straight radiance, then those curves are moving up and down with temperature. The shape of those curves is changing slightly. But the ratio of the energy emitted from a natural surface to an ideal surface stays the same. So this emissivity doesn't change whether I'm measuring it at 20 below zero or at 500 degrees centigrade. This emissivity of quartz won't change. Okay, so to quickly come back to our vibrational model, what's happening is, if I can explain this sort of quickly and simply, deep inside the material, I've got all these motions, and it's generating this Planck-like distribution of energy. As that energy tries to escape from that crystal, it's being absorbed, preferentially absorbed at frequencies or wavelengths that correspond to these harmonic frequencies. Okay, so this particular frequency that corresponds to a wavelength of, say, 20 microns, that's one of these harmonic frequencies. So the energy that's trying to get out is preferentially absorbed. The atom likes that energy. It vibrates at that energy. It takes the energy out of the wave. And so what we see coming out of the surface, there's a deficit of energy at that particular frequency. So the point of all this is that these infrared spectra, which we can quantify remarkably well, you can get right down to the basic physics of vibrational modes and all this other kind of stuff. There's this beautiful quantitative basis of all this. But for remote sensing, what we really care about is that because every known substance on the planet has a unique crystal structure, it will therefore have unique vibrational modes, and it will therefore produce a unique infrared spectrum, okay? So I can make a list of minerals that mean something to a geologist: quartz, clay, olivine, calcite. This is what they make concrete out of. Each one of these minerals then has a very unique and diagnostic infrared spectrum that's based on its internal crystal structure. It turns out that a lot of what we know about the chemistry of and the crystal structure of materials has come over the last 100 years from studying their infrared spectra, okay? All right, and it turns out you can get incredibly detailed with this. It's one thing to say, this mineral is sort of different from that one, but these are examples of minerals that I don't expect you to know, but these are classes of minerals which are very, very similar. But if I start replacing, say, the iron atoms with magnesium atoms, that changes the fundamental frequencies because the mass of those atoms is changing, the frequency of the system is changing, and these absorption bands shift around. So it's a very diagnostic tool down to very precise levels of what the crystal structure of the material is. And the beauty of an infrared spectrum from a remote sensing point of view is I can measure from orbit around Mars the light that's given off, measure this spectrum, and determine what the composition of the surface is. Okay, I don't have to touch it. I don't have to put it into an instrument. I don't have to do anything to that surface. I can just measure its infrared spectrum and get a very unique identification of what minerals on the surface. And we've done that, and I'll show some examples a little bit. Although I've spent the last 25 years studying Mars, and I think I only have one slide in here on Mars. So for better or worse, if you wanted to hear about Mars, you're going to be disappointed. Okay, the other thing that you get from an infrared measurement, which I think is extremely interesting, is this idea of temperature, okay? The spectral information is telling us composition, but the total magnitude of the energy emitted is telling us temperature. The hotter something is, the more it emits. Okay, that's fine. But we can take that information and use it in a very quantitative way. You can develop very sophisticated models that predict the temperature of a surface as a function of time of day based on the physical properties of that surface. Its grain size, its conductivity, its subsurface layering, whether it's a metallic material. You can put all of that stuff into a model and predict how the temperature will vary with a time of day. So for example, large rocky materials will hold their heat really well at night. They've stored a lot of heat during the day, and then that heat comes back out at night. So rocky materials will stay warm at night. Very fine-grained sand and dust materials, we're not able to conduct heat into the interior. We're not able to store any heat. So at night, that upper layer cools off very rapidly, and there's no stored heat to come back out and warm the surface. So we get these diurnal curves that vary significantly on whether a material is rocky or fine-grained. So for example, here's a place on Mars that here it's very warm at night, okay? And here it's relatively cool during the day. We can go into these thermal models, measure those temperatures, and say, okay, this is actually bedrock. This is pure solid rock sitting on the surface of Mars. This stuff that was relatively cold at night and heated up during the day, that's, say, millimeter-sized gravel. So you can actually get very quantitative about this and be able to pin down the particle size of surfaces to, I can tell whether it's millimeter gravel or 2 millimeter diameter gravel based on these very precise temperature measurements. Okay, so from the infrared then we get composition. We also get some indication of the physical nature. And then finally I wanted to come back. So that was the vibrational spectroscopy, the low energy end. If you remember back, I was talking about the moderate energy UV visible light. That's where the photons have enough energy to actually interact with the electrons. And if you remember back to an energy level diagram of hydrogen or sodium, the electrons in the cloud around an atom are, they're at a ground state. They can be excited to an excited state. If the energy to go from a ground state to the next level up is equal to the energy of a photon, then what happens? That photon excites the electron. Oftentimes, there'll be a collision within the atom. Instead of the electron just jumping back down again and giving off a photon, it will, before it can do that, another atom will collide. That energy that was stored in the higher energy state is converted to kinetic energy of the atoms. And so again, if I took a flashlight, shined it in, if I have light whose energy corresponds to one of these energy states, it'll excite the electron, and what comes out the other side will be, I won't see that photon coming out the other side, okay? This is the basic concept of why objects have color, okay? This is what's going on in dyes and going on in the things that you see with your eyes. It's photons exciting electrons and being removed from the beam. Okay, and just some quick examples. This is down in the visible light, so this is half micron, 1 micron, 2 microns. Our eyes end up cut off here at about 0.7 microns. These absorption bands are due to electrons being excited within atoms within the material. So a lot of remote sensing, near-infrared remote sensing that's done has to do with these electronic transitions that are going on where photons are being absorbed and used to excite electrons. The problem with electronic spectroscopy is there's only a very small number of elements where this process actually occurs at these kinds of wavelengths. And specifically, it's the transition metals. And I know I was crummy in chemistry in high school. I can never remember what transition metals are. But iron is one. Copper is a good example. Okay, so basically, this kind of spectroscopy works in nature in iron-bearing minerals. Okay, well, if you think about driving around in the deserts, most of the color that you see is yellows and oranges and browns and butterscotches and tans. Almost all of that is due to iron-bearing minerals or iron stains. And those stains, those iron-bearing minerals have colors because of these electronic transitions. If a mineral doesn't have iron in it, like quartz, for example, that's why it's colorless, because there are no elements in there that can interact with the photons and have energy levels at the right appropriate levels to absorb the visible light. Okay, so it works great for iron-bearing minerals, but the world isn't necessarily covered with iron-bearing minerals. Okay, all right, so that's the end of the physics lesson. Let's look at some real examples. And again, what I'm going to try to focus on for the next little bit is things that you're not used to. I mean, things that don't have to do with looking at the world in visible light. This is a Landsat image. Landsat is a spaceborne imager. It has 7 bands. You can use bands 1, 2, and 3 and construct a natural, normal light image that you would recognize. This is an image of a delta, I think in the Amazon region, constructed of some of the other bands. Okay, think the wavelengths that your eye doesn't see. But I would still say, this is pretty close to what we've been doing, humans have been doing all along, looking at the world. Okay, so that's sort of what the world would look like. I want to show another example. This is Phoenix. This is a more or less normal Landsat scene. It's not quite red, green, blue. It's green, red, near infrared. I think many of you are familiar with this. This is a false color image. We've taken each of the wavelengths and shifted it down one. So green is displayed in the red gun of this projection. red in green, and near infrared in red. As a result, vegetation, which is very bright, very reflective in near infrared light, because it interacts really well with the electrons are easily excited, vegetation shows up bright red, okay? One of the things, though, that you can do if you want to emphasize certain things and bring out certain compositional information, you can actually make ratios of those bands. So instead of just making a color image, I can take two bands and ratio them. And so this is an example of taking one of the bands where vegetation is very reflective and one where it's not, making a ratio of that. And so here, any vegetation is very clearly identified as being in this ratio. You also see other things that show up. And my point is not to dwell on this, but to simply say, you see certain patterns and certain information if you look at just a, quote, normal color image. You see other information and other patterns if you start ratioing the images or in some other way trying to extract information from them. So for example, clear differences, say right here, between urbanized and non-urbanized actually can show up better in some of these ratios than they do in the original, just in the color image. This is an example of what I said about what the world would look like if you had infrared eyes. I've taken this set of spectra, and you can fly a spectrometer, but they're big and expensive and complicated, and they're hard to get to work. I can also build a camera, an infrared camera, that's relatively straightforward and only has 3 filters. And if I put one of those filters at 10 microns, one at 9 and one at 8, and took an image, and then I displayed the emitted energy at 10 microns as red, 9 as green, and 8 as blue, then for example, if you look at quartz, it's emitting a lot in what then becomes the red band, not much in green and not much in blue. So in a false color infrared image, that quartz would look red, okay? Similarly, if I take a mineral that's bright at this wavelength and is absorbing at these 2 other wavelengths and display it, it's going to look blue, okay? So if I flew an infrared camera, 3-band infrared camera across the desert, instead of, you fly along, you look out the window, the world is brown and gray and tan. In the infrared, this is literally what the world would look like if you had infrared eyes. And to a geologist or someone interested in the composition, the nature, the makeup of the surface, this is what you'd see. And this is basically a geologic map of this mountain range without having to do anything at all. I mean, geologists spend years detailed mapping to try to find all these different mineral deposits and rock outcrops and different types of material. This infrared image is essentially giving you that information instantaneously. I can see quartz-rich sands, and I can see volcanic rocks, and I can see gypsum-bearing salts, et cetera, okay? So it's a tremendously powerful tool for mapping the composition of the Earth's surface. This is an example of the surface temperature in Scottsdale, Arizona. Bright is warm, and in this case, pretty darn warm. At those surface temperatures, we flew this in August, those surface temperatures are probably 140 degrees Fahrenheit. Cool, dark is cool, and it's pretty darn cool. The cool temperatures are probably about 80 degrees Fahrenheit. So where would you want to have your house? Next to the 140-degree baking hot asphalt and dirt, or next to the 80-degree nice cool lake and golf course? Well, okay. But the point is, these infrared images actually provide a tremendous amount of information about temperature, which feeds into all sorts of other important things. In Phoenix, we're trying to actually use these to measure lake temperatures and swimming pool temperatures and calculate evaporation rates and how that's affecting the humidity. And there's all kinds of environmental impact of all of these crazy golf courses and all these lakes that show up extremely well just by looking at the temperature effect of those things. And I'll just touch on this. This is a really detailed spectrum, again, from about 20 microns, sorry about the units, down to about 5 microns. So it's an infrared spectrum, extremely high resolution, looking at gases in the atmosphere, in this case, the atmosphere of Mars. Even down, if you look at that box, you can build spectrometers that have that kind of resolution. This is how we're monitoring trace gases in atmospheres. So there's a tremendous amount of information that you can get about the composition of the atmospheric gas. When I was talking with Michael a little bit, one of the topics that came up about what can you do with remote sensing from a practical point of view, a lot of the times you're dealing with a scene that was taken looking through the atmosphere and you're trying to separate the atmosphere from the surface. If you're just trying to make a beautiful map of the ground, you want to remove the atmosphere. If you're an atmospheric scientist, you want to remove the surface, okay? So I used to call this atmospheric correction, but the atmospheric guys got annoyed about that because it was, so now I try to say we're separating the two. There's basically 2 ways to go. You can do very sophisticated radiative transfer modeling, and there's packages that do that, where you put up a radiosonde and you measure the temperature and the pressure and the water vapor and all this stuff, and it goes into an incredibly complicated model, and you try to remove that signal from the ground. Or you can do scene-based approximations, which in the real world are the only practical way to go. And there's a bunch of ways to do that, and I'll just show a quick illustration. This is an infrared scene, one of these beautiful 3-band infrared color scenes. And this particular scanner is a line scanner that looks out in both directions. Okay, so looking straight down, we're looking through a certain amount of atmosphere. Off to the side of the image, we're looking through almost twice as much atmosphere. And as a result, you see this band of yellowing down the side. Okay, this is an example of this types of problem. A really simple way around that is to say, I'm going to assume that statistically the ground is sort of randomly distributed. So what I've done here is I've just taken a column average of the entire scene, and those 3 lines then represent a single line that's an average of all the lines in the image. And you can see the effect of the atmosphere with this absorption that's going on over on the edge. I could try to model that, or I can be really simplistic and say, I'm just going to take this signature and subtract it from every line in the image, okay? So this is just a simple scene-based example, and you can see what just something even that simple has done. This material, which looks yellow in the original data, suddenly looks like it's supposed to do in this scene-corrected data. So there's a lot of very simple ways that people have devised over the years in a practical sense to separate the tremendous amount of information that's in these images. Okay, let me just quickly show, I'm not a radar expert, but I didn't want to talk about remote sensing and not mention radar. There's a tremendous amount of information in radar as well. Here what you're seeing is all of this bright material is basically man-made, metal-rich material. This is a scene from a radar experiment that was flown in the shuttle, again over Scottsdale, and you see natural desert, watered fields, but this incredible signature from the metal in the city. With radar, you can transmit these electric waves. You can transmit them this way and that way. And which way you transmit them has a huge effect on what happens. So for example, the main difference between those 2 scenes is whether or not the wave was transmitted vertically or horizontally. In the first case, it's vertical. The electric field in the wave was oscillating vertically. And so where I had electric power lines, there was very little interaction. In the second case, the wave was oscillating horizontally, where I have electric power lines. I get a very strong interaction, okay? So one of the beauties of radar is you can actually tune you can design your experiment so that you can pick up different things. And this is just an example of 3 different radar images combined into a color image with a fantastic amount of information in there. Okay, let me just quickly go over a couple of applications. This one I've showed an example of. This is, again, an infrared multispectral image of some mountain range in the Southwest. Remarkably, very few people use this type of information, even today, to try to do compositional mapping of the world. This is what we have. This is the type of instruments that we've flown to Mars. We have better maps of Mars than we do of the Earth, of trying to look for rock types and minerals on the planet. One of the things you can do, in addition to make pretty images, you can actually look at the spectral signature. You have all this information. You can take that spectral information and try to classify the scene. So for example, this is a Landsat image of Phoenix. Then this is taking that spectral information and classifying the scene. I'm going to zoom in on, this is the airport. So you can make this, again, it's an automated tool. You define what the rules are, what each of your classes, what it consists of, what type of spectral signature it has. And so we're looking at cultivated grass, vegetation, commercial compacted soils, water, asphalt, concrete. So you can make these classification images of a city that then you've extracted a lot of information about that city, and you've done a lot more than just make a pretty picture of the city. I've actually got information that I can use to study, for example, study the city over time, see how deserts being converted to agriculture, agriculture into urban use, et cetera. Okay, the other thing that you can do with remote sensing of cities in particular is look at temporal changes. This is an example of Beijing from a very early 1978 relatively low resolution version of a Landsat instrument. This sort of ugly gray color here is most of the urbanized part of Beijing. In this false color image, fields and vegetation are showing up red. And it doesn't take much to sort of note the difference between 1978 and 2004. In that same area 2 years ago, there's virtually no agriculture or vegetation left in this region. Okay.
We're seeing
Yeah.
a seasonal difference there too.
In this particular case, there is a seasonal difference. In an ideal world, you certainly wouldn't want that. But one of the problems, I was talking earlier, it's remarkably hard to go back very far, even from the satellite data. Oftentimes, we only had one image a year that was even acquired. So, but you're right, and that certainly complicates the whole situation. And in particular, in China, where their cities are evolving quickly, it's remarkable how much change is occurring. Shanghai was a relatively small city surrounded by vegetation 30 years ago. Today, it's grown dramatically. I think I have one more example. Hong Kong. So you can use remote sensing in the time domain as well to really look for temporal changes in the Earth's surface. You hear a lot about things like deforestation in rainforests, but some of the most dramatic changes are occurring around cities as they are growing spectacularly. From the nighttime temperature, you can study things like urban heat islands. I'm assuming you've heard of this. This is a nighttime temperature of image of Phoenix. And a couple of things are apparent. First of all, where are the warmest parts of the city? Well, they're the roads, the buildings. That huge bright blob up there is the airport. Okay, it's pretty easy to see where the man-made sources of heat are. What's interesting, though, and it sort of surprised a lot of people, is how warm the natural surfaces are as well. Okay, so sometimes converting from if you converted this mountain into houses, you might, in that particular case, actually lower the temperature. Okay, so studying heat island developments in cities is complicated, and these types of infrared data are extremely useful. This, for example, is the Gila River, which doesn't flow at all. Okay, there's no water in that river at all. It's all underground. But there's enough underground moisture flowing through this dry, quote-unquote, dry riverbed that the evaporation from that moisture is cooling off the surface. Okay? So the point here is there's a tremendous amount of information in these infrared images. Another quick example, this is a handheld infrared camera looking out at Tempe Town Lake, a small little lake, man-made lake, just real close to ASU. And I wanted to use this to illustrate well, I guess I won't. I'll have to come back to it. So even simple, you don't have the fancy aircraft or satellite infrared imagery, just handheld infrared cameras now are becoming inexpensive enough that you can begin to put these in strategic places and monitor things like water temperature and surface temperature and road temperatures, et cetera. One of the points that I was going to make is oftentimes, for those of you who are trying to do any type of scene classification or automated scene identification, one of the things that we have real trouble with is telling water from asphalt. They're both really, really dark. And in fact, there's cases of automated rovers that drive out onto a lake because it's smooth, it's dark, it looks like a perfectly nice surface to drive on. The one place that water and asphalt really differ from is in their temperature. Okay, so if you had a temperature information as well, then suddenly identifying two dark things is trivially easy. Okay, so one of the things that we're trying to do is identify water based on temperature. You can also do things like monitor volcanic eruptions. This is a satellite image in the visible with a superimposed infrared image. It's an active eruption taking place in Kamchatka from space. And so for volcanic hazards and volcanic eruptions, obviously the infrared's a powerful tool. Weather gets a lot of attention, as well it should, but there's other things that go on in the atmosphere besides just rainfall and cold fronts. This is an example, and this is the western coast of Africa. That's Gibraltar, and that's Spain for scale. So this is a huge piece of Africa and part of Europe. And this is a big dust plume that's blowing off of the Sahara Desert. Okay? These dust plumes are not uncommon, and oftentimes they reach all the way across to North America. You can easily detect Saharan dust in the air in New York City, and from space with remote sensing, you can track these things. You can see them coming. On the other side of the world, you see the same sort of effect. This is, again, dust being blown off of the Chinese continent and headed east. So there's a tremendous amount of things that go on in the atmosphere besides just weather. Okay, so again, just to plant seeds of things: pollution, aerosols, volcanic ash, volcanic dust. These are additional things that you could monitor from space. Just a couple more applications, some things that we're doing that I wanted to mention. as part of a NASA activity a couple years ago, a few years back, I started up a thing called 100 Cities Project, whose goal was to try to monitor 100 cities around the world. And in doing that, we were trying to collect all kinds of information, not just satellite data, not just remote sensing data, but socioeconomic data, geographic data, land use data, zoning data. And what we're finding is when you start combining those other levels of information with the imaging data, then suddenly economists and sociologists and all kinds of folks get really interested in these data sets, okay? And so for things like Google Earth that have this beautiful imagery, what we're trying to do is look at other pieces of information that you can add to that, whether it's things like the depth to the water table, well logs, traffic accidents, air pollution, air quality, thunderstorm tracks, whatever. There's a tremendous amount of information, much of which you can get remotely, that you can add to the image data. And this is just an example where we've built up this system that's trying to use some of these satellite data, in this particular, in our case, temperature data as well, to add to the existing visible imagery. One other thing that I just wanted to mention, this is something that Michael actually was working on back when he was at ASU. This is an example of 6 or 7 global data sets that we have for Mars. We have a total of 57 of these, and everything from mineral type to rock type to where dust storms have occurred to changes in surface albedo to nighttime temperature to elevation data. What you find is when you put this 56 data sets together, then suddenly people are doing very sophisticated research on these global data sets, okay? And I don't think any of the ones that are in our set of 56 are classic visible remote sensing. They're almost all thermal, radar, topography, laser, et cetera. So I think this is an example where on Mars, we're probably doing more sophisticated combinations of remote sensing data than we're actually able to do here on the Earth. And I think you could easily develop these very similar types of data sets here for the Earth. Okay, I think I have, okay, I wanted to show one other example. This is an example of a infrared spectrometer. So it's that full spectral resolution that I showed for the Martian atmosphere. You can actually develop these now where they're imaging systems, where each one of those pixels is a full 2,000 point spectrum. So for each time step, for each pixel, I can then take that full spectrum and identify, in this particular case, gases that are being released, okay? So for pollution monitoring, for looking at what's coming out of smokestacks, for what's coming out of cities, this next generation of remarkably sophisticated imaging hyperspectral instruments, it's a tool and a technique which I think is going to have tremendous potential and get a lot of use. Only within the last few years have we been able to build instruments that are capable of doing this, build computer systems that are capable of processing these data. But I think it's an extremely exciting way of looking at the world in a much more complex terms than just with RGB. Okay, I think I'm going to skip this one and just close with a couple of other thoughts. I just came back from, I spent last week at a NASA conference with folks who were looking at what astronauts are going to do when they go to the moon. And without getting into the detailed politics of that, in NASA's mind, we're going to send astronauts to the moon, and the scientific community was then tasked with what are they going to do when they get there, okay? You could easily argue that you have that problem backwards, but so I was tasked with what could you do observing the Earth from the moon, okay? And my first thought was that's really stupid. We have 25 Earth-orbiting satellites, and we have geostationary weather satellites, and we're looking at the Earth just fine from the Earth. But it turns out that there are actually a few interesting things that you can do. For example, this is the Earth from geostationary orbit. This is the classic weather satellite view. It turns out those things are pretty far away. They're 30,000 kilometers up, but they're still close enough that you don't come close to seeing the entire Earth. So for example, you can't see the polar regions at all. Up at the top, you can see Alaska and the Aleutian Islands are just about disappearing over the limb of the planet. Viewed from the moon, that's what the Earth would look like at that same at that same time. And so there's two particular things that are of real interest. And I don't know, you may know this. The polar routes from North America to Asia always go over the Aleutian Islands. And oftentimes they go over in the polar night. And the Aleutian Islands are the single most volcanically active place on the Earth. And at any given time, there are a dozen or so volcanoes that are erupting. Twice, on two separate occasions, 747s have flown into ash clouds unknowingly and had all 4 engines stop. In both cases, those engines were started before that airplane crashed, okay? But this band of islands in the Aleutians it's a dangerous place to go. So one of the things that people have talked about is putting sensors up that are constantly staring at at that chain of islands, monitoring volcanic eruptions as a heads up for jets not flying through them. The other thing you can do, clearly, the poles are extremely interesting from a climate change point of view, and we don't have good continuous coverage of the poles. So there are actually things that one could do from the moon, looking back at the Earth. And it turns out with a modest-sized telescope, you can actually see, you can get sort of 500 meter per pixel imagery of the Earth from the moon, okay? These are some examples. I won't go into them, but these are some of the examples of the infrared mapping that we're doing on Mars. And again, I think it's a sad statement to say that we probably have better data on the composition and the physical nature of the Martian surface than we do the Earth, simply because we've flown some more sophisticated instruments to Mars than we've flown to the Earth. Yeah, right.
Also less nasty plants on Mars too between you and the rocks.
Yeah, there's definitely fewer nasty plants on Mars than there are here on the Earth. And as a geologist, I do think that's a good thing, but not everybody does. Okay, and so I think the summary then, remote sensing across the electromagnetic spectrum and through time, I think has a lot of potential for providing a lot of quantitative information about the world that people are going to want more and more access to and are going to, I think, be able to come up with more and more applications for how they actually might use that data. And I'll certainly stop there, and I apologize for droning on like a lecturer. I will certainly take questions. Yeah.
When you were discussing emissivity, you described a process that I think corresponds to incandescence. Is there anything useful in fluorescence?
The question was, the comment was, in describing emissivity, I was describing something that was similar to fluorescence, and that certainly is the case. you can, you get these waves and they excite things, and you can be excited and then cascade back down, or you can be excited and, and fluorescence is one of those processes where waves are excited or absorbed, electrons are excited, and then as that electron comes back down to its original ground state, it can give off photons. If it comes down in a series of steps, then it actually gives off photons whose wavelength is different than what it absorbed, hence fluorescence. And yes, there's a lot of information in that. Typically, you illuminate in the ultraviolet, and materials then re-emit or fluoresce at visible wavelengths. But there's a lot of information in that. I find scorpions in our backyard because they fluoresce at night, and so you can find them easier than. But that's a good example of another way of looking at the spectrum. Yeah.
So I guess seriously, what fraction of the Earth's land surface can you map geological maps from? Because there's not too many plants. Okay.
The comment was, what fraction of the Earth's surface can you map geologically without the interference of plants? It's Southern California, I can do fine. Arizona, I can do fine. Rainforest, no. Northeast forest, no. It turns out, even if you have like 20% of the ground covered with plants, or 30%, 40%, you can still get a really nice signature through it. One of the interesting facts is that huge parts, from a human perspective, large parts of the population of the Earth live in relatively arid places, okay? So monitoring those, mapping those is really useful. The other thing, from a climate point of view, the arid places on the planet are the ones that are undergoing the most rapid change. We can detect changes in vegetation, so you can detect desertification, if you will, in arid regions. The polar regions are extremely interesting, looking at alpine glaciers and seeing how they're retreating. So there's a lot of really interesting processes that you can map that are going on in places that don't have a lot of vegetation. On Mars, you could do it on the Earth.
Which implies that there is no material that is identical to another material in the infrared spectrum but differs in the ultraviolet.
Yes. I guess the point I was trying to make, and I didn't make it very well, was that every material by definition, has a unique crystal structure. It's made up of a unique set of atoms that are bound together in a unique way.
So this is not valid for characterizing amorphous material?
You can identify that it's an amorphous material, but things like glasses, for example, don't have nearly as complex an infrared spectrum as, say, a crystalline material. But so any crystal, mineral, plant, man-made, whatever, if it's got a crystal structure, it will have a absolutely unique infrared spectrum. Okay. And if you have enough, and enough depends on what you're looking for, but for geologic materials, for biologic materials, several hundred spectral bands is plenty to be able to identify those uniquely. All right. Thanks very much.